Hello everyone, and thank you for joining us again. It is Ivailo Vasilev from AstrumDrive Technology, and we have Nelson Bolivar on the line as well. He's the chief scientist, and he's also leading the research we do for the warp drives. I have to apologize that we didn't do a recording for quite some time, but we were very focused on writing several articles. One of them we're going to share with you today. And because we didn't want to disclose things which were not published yet, this was the reason we didn't do the recording. But with this recording, we're currently going to do for this article, we're going to continue our recordings later. We have two more articles which are like submitted for publications, and whenever they're out, we're going to make video reviews for them as well. And after that, we're going to resume our normal sprint review sessions. And having said that, Nelson, please go ahead. It's your meeting now. Please tell us what we published and where, and what was the idea of this article.
Hello, Ivailo. Hello, everyone. It's good to be here again. And yes, we have a lot to say. But let's focus on this article in particular. This is something that we have been working for almost 1 year so far to figure out a metric, space-time metric, which with this specific symmetry, spherical coordinate symmetry, and that can give us more insight about what happens with warp drive. And there is a lot to say about this article that is in the article, and a lot to say still about some things that are not in the article, which is part of our next research and the things that we're already working on. But so let me go on the article and more or less briefly we go on here by explaining what people already know. People already know this question one here. This is the line element proposed by Alcubierre in the 90s, and this is quite simple. And just let me summarize very quickly. This is what we have here is the line element in Cartesian coordinates, and we have here in this part what we can call, or we usually call, warping in the x coordinate, in the x direction. And this warping is given by this modification that you see here, that is partially is have this the dt here, which means that we are mixing partly what happens in space with what happens in time. So this is like we can say a non-diagonal metric. And there is a function here. This function f is a function that is called form function. Sometimes it's called the shape function, and we will see it again and again in the whole document that we have here. So basically, we took an idea like this one, and what we did was, okay, let's make some sort of generalization to write down this in spherical coordinates and see what happens. So it seems like we're basically it's like we want to change the symmetry of what we are doing, which people might say, well, basically what you have to do is change the symmetry of the shift vector that you have, and that's partially true. That's partially true, but it's just the mapping. The change of coordinates implies changing coordinates itself, but also implies changing the function. And what we did here, what we already published is, wait, is this change in coordinates? It doesn't really says how the shape function is going to be. So we want to know how the shape function or the form function is going to be, so we can have some effects, warping effects, and some physical effects, and what is the effects that we have on the content matter that we have. So in order to do that, we say, well, this goes into the into the references that are already public, and we found that Bobrick last year, no, in 21, they published a very nice article where they figure out how to construct in general warp drive metrics, warp drive line elements specifically. And so basically what we did was, okay, let's take this Bobrick's recipe and construct a warp drive that has this spherical symmetry that we want. And we want spherical symmetry for a lot of reasons. One of them, I think, is the most important one. Is like the in spherical symmetry, a lot of things are easier to see. By a lot of things, I mean it's easier to include matter. The equations usually simplify a lot because this is like the natural symmetry that you have. Is you have some sort of object or some physical system that it will have a gravitational field in a sense. So this is like the natural way to describe this. So okay, let's write it down in this symmetry, and we went on that. We went on that. Basically, the idea is like you have a very general line element, like this one. It doesn't matter the details right now, but what you have here is like something similar. If you see here these terms, is similar to the terms that I just showed you of the Alcubierre ward drive. And but this general theme that what you do is like you find out what are this turn and this turn should be, and this is what we call a one-to-one mapping between two observers. This is well defined in Bobrick's article, and the mapping that we find out this is good for us is this mapping here. So basically, we did all this. We did some very simple algebra, and you basically end up with this line element here. This is the one that we propose, where this beta here is basically the same f function that we have in Alcubierre, something similar, multiplied by the velocity. But what we agree was that let's not say that this is necessarily just velocity times the form function. Let's say that beta is just a function. It's a function of time, yeah, a function of all the coordinates. In this case, is the r, mean the radius, and the both angles that are related to the spherical symmetric coordinates. So basically, this is the metric that we find out. And this metric, we start asking questions to this metric. This is a question here. The first thing that you have to do is once you say this beta is a general function, let's plug this into the Einstein's equations, the field equations, and see what happens. So what we obtain is this one. This is the definition with Einstein's equations using where we're using units where c the velocity, the speed of light, and the Newton constant is equal to 1. And in these units, these are the components of Einstein's equations that we found. So basically, okay, this is like this side of the Einstein's equations, the left-hand side. And now that we have this, which is, well, it requires some work, some simplification. Maybe sometimes it's cumbersome in a way. Then you have to figure out what is on this side. And the basically, our goal was, well, you have the left-hand side. Let's propose something for the right-hand side, and then see what are the conditions on this very general function beta that fulfill this. And of course, what we want to see is like what happens with several types of matter that we can put here. And that's what we did. So we propose, okay, let's use as in general what we call a perfect fluid. To start with, a perfect fluid. A perfect fluid is just a fluid that has some energy density and have some pressures, but all the pressures in the system are the same. I mean, if you have pressures, you can have tangential pressures, tangent pressures, you can call it, that are tangent to the motion, for instance, onto some observer, and also some parallel pressures that you can have. But in this case, all of them are the same. And this is what we call a perfect fluid. It's not the most simple one. The most simple one will be if the pressures are all zero and you just have the density energy in the system. We don't want that. And so let's say what happens. So to construct this, what is called the energy momentum tensor, uh, you have to take into account what the metric is. So you see the construction here is you see, okay, the metric is involved here. So this is the energy momentum tensor for this space-time that is consistent with this space-time and that includes density and pressures. Knowing that, then we just plug this energy momentums here, and you basically see what are the components. I mean, the 0, 0 which is the time component, then it is equal to the proportional to the t00, and so on. And you see what are the components that are different from zero. That's one thing we should do. And I'm going to ignore this for a moment, but this is what you get at the end. Basically, three independent equations. That's it. So after fully simplify the whole thing, you get just three different equations with a simple perfect fluid. And that's very amazing. I mean, if you do the same for Alcubierre's or to other symmetry, you get more than three equations. So this is like a very nice simplified system of equations that you have to solve. And one thing that is remarkable here is that if you see this equation here, and I'm done coming back, it's related to this one. This equation, this is 24, comes from the fact that you are making this uh, basically you are multiplying by the velocities. These velocities are four velocities that point only in time direction, which means basically that you are looking here, which is at the end here, is just the time part of the Einstein's equations. And this part is what everybody finds in the literature when you want to see what is the density energy of the system. And if you review Alcubierre's work, you will see that what they find is like they find this equation here, and they find their version. In their version, they have density energy here, some derivatives on the other side, and a minus sign. And this minus sign is always there because everything else is square. So the minus sign is not going to change. So that's basically the problem of negative density energy in a nutshell that they obtain. And if you see our equation here, we don't have that. We don't have the problem in principle. Of course, there are some things that we have to say to be really sure about this. But basically, we have this square, but inside here you see that it's just the beta and some derivative of beta with respect to time. Then what I mean when I say we have to be careful and say, oh, this is always positive. Well, it's not necessarily positive. And one thing you have to do is very important is you have more equations to consider. This is just the temporal one. Basically, it's saying that you have this part and the t00 part, but you have all this other one here, and you have put all this together here, and each one of these is equal to their part. I mean, this G01 is equal to C01, and G11 is equal to T11, and so on. And you have to consider all the equations. If you consider all that, this here, we have a different shape. But the shape it has is not complicated, and it's not really important in this point because this is part of what we did next and we were working on. But basically, it's always positive. It has positive and negative contributions, which is great. It's great because basically what we're figuring out is like our density energy in this system is not necessarily always negative. It's one side is finite, so it's different from zero in general, and on the other hand is could be negative, of course, but also can be positive. And this is a breakthrough in this sense because we, under just changing the symmetry of the system, uh, we obtaining uh, density energies which are possible to be positive, and that's basically the breakthrough that we're talking about here. Of course, that said, we went to explore the energy conditions of the system. We have now this. We have a version which is independent of time, that which you call the stationary system, and we obtain some nice results here that you can check out in the article. The article is open access, by the way. You can check it out whenever you want, and you find the link in the website of AstrumDrive. Uh, the point that it's like we want to check the energy conditions because that's good. What we just find before is good. Oh, you have positive density energy, but that's equivalent basically to the weak energy condition. That's the same. What we did above is just the weak energy condition. And that's good because we are at least partially satisfying this for some uh, regions of space of parameters that we can have in the system. But what about the other energy conditions? What are these energy conditions? Well, these energy conditions are not really part of general relativity theory. This is something that you use as an additional thing to trying to make sense of some physical requirements on the systems that are important. We're talking about causality, yeah, we're talking also about not having strange matter in the system. So we check the energy conditions. Not all of them have to be fulfilled all the time. Indeed, if you have read some of the work that has been done in the past about energy conditions, some of them are violated, some of them not. Some of them are violated sometimes, and the other are fulfilled, other ones. So we want to check what is the story with our metric, and we found that basically all the conditions are fulfilled with the exception of the let me check here, the strong energy conditions, which I don't find it here. Here is, with the exception of the strong energy conditions, we have something that is related to the pressures, and we find out, okay, we don't have uh, of all the energy conditions fulfilled. That's not a problem. That's not really a problem. In fact, if I have to say something, most of the approaches that are concerned about the energy conditions are uh, directed to the weak and the null energy conditions are, in some sense, the most important ones. Not the only ones, but the very important ones. Anyhow, basically, if we do that, and then we wanted to know more about the system. What is more? Well, I told you before, we have this energy momentum tensor that has all the pressures are the same. We want to change that. We want to figure out how a matter content will look like if we just have different pressures. And we decided to go in very nice ways, which is, let's propose a generalized energy momentum tensor, right? This is just a fluid, a general fluid. And then plugging that, this general momentum tensor, we can see, depending of what is in the this side of the equations, by saying, let's put some general T mu nu here, and then look what the relation with this G here, the Einstein tensor, is going to tell us about what are the possibilities that we have here. We are not really just imposing it's a perfect fluid or some sort of fluid. This the equation tell us what is it that we can, what is it that is allowed to put in this energy momentum tensor. That's what we did, and we follow a very nice article. This is not our idea. You can find Santos did it before a couple of years ago, but we did it and we find out that, okay, this is like an ansatz of the energy momentum tensor, which might include this off diagonal terms and all these terms, and we have to figure out what is this T and this B and this A and this C here, and this uh, tensor here allows for heat transfer, different pressure for the systems, and the density energy, of course. Basically, those are the things that are present there. Oh, yeah. And then we figure out, and for consistency, basically, which is seeing what can we tell about the energy momentum tensor due to this coupling with the Einstein tensor, we find out that these are the values that we to have to put to A, D, B, and C. So basically, what we found is like well, A equals Z equal PR, which is the radial pressures, and B equals C to the the tangent pressure, and nothing less, and nothing else. So basically, nothing else means that we don't have heat transfer in this case, which is okay. It's okay. So it's not consistent with the Einstein's equations in this case. And well, but given that, we see that, okay, we have these different pressures, which means that we have an anisotropic system. And we go on again and put together the energy momentum tensors and find out the field equations, which is again this one. And we found these equations here. the equations, these three ones here. In this case, also, we have to add that we added, for the sake of completeness, the cosmological constants here without giving much importance to it, just to keep it there like an additional term that could be in the system. It is allowed to be there. We don't know. We're not really saying that it's the real cosmological constant of the cosmos, but this is an additional term that we can put there. And if you see here that basically what we obtain is a system of equations, again, three, but now as a difference, we have this term here, this pressure, radial pressure, and this delta here. This delta is the difference between these two pressures. And this delta is what we call the anisotropy factor of the system. This tells you whatever you want to know about how anisotropic the system is. So in this difference here, well, you can have that this difference could be positive or could be negative, depending on how the pressures in the system are. And these three equations, again, given this delta here, tells you that you are allowed to have positive density energies in the system. Again, even if you ignore completely the cosmological constant, you have that this density energy is going to be at the end depending of the radial pressure and of this delta. And we have positive term, negative terms, one term that is proportional to this delta, which is could be negative or could be positive, depending on how the configuration of the system is. Uh, and with that in mind, it means that you have, again, a region of parameters where you are allowed to have positive energy um, solutions of the system. And we again this you say, well, let's check what are the energy conditions, what happens with the energy conditions here. We did it, and basically we find out that the weak and the dominant energy conditions are the same. The strong energy conditions now is, you see, there is a contribution of this uh, uh, tangent pressure here, which if it's zero, is not there, or could be that it's just tangent pressures is equal to the radial pressures that you have these two to the same term add up. And um, and the null energy conditions also is implied in the system as including the pressure, just the radial pressure and not the tangent pressure. We want to remark that also in the paper. So the basic idea, if I have to summarize here, is like the whole point of the message that we want to send. We want to send is like these solutions allows for this equation 46, 47, and 48. And this is great, guys. This is just great because then you want to solve this system of equations. I mean, I'm talking about what are the betas that allow for this to be, this set of equations to be fulfilled. And of course, this is a system of differential equations. It is nonlinear, and you have to work it out. And well, it's part of the work that we're already doing, and we are on the way of publishing. And that's basically the idea. I think if you have more questions, please download the article. Let me just go to the very beginning. You can see again where it's published, and just download it and just write us with any questions you want.
Nelson, thank you very much. It was a great overview. So let me point out that the article was published in Physics Journal C, which is Q1 journal. This is one of the best physics journals in the world, which is heavily peer-reviewed. So all the research we're showing to you guys is something which is already checked by the lead scientists in this area. And Nelson, I just want to summarize a little bit my understanding about the spherical warp drive metric. So basically what we're saying is that the spherical warp drive metric allows us to have some favorable symmetry. So it's significantly easier to work with the spherical warp drive metric in comparison with Alcubierre. And this is what is allowing us to come to these conclusions easily, because we have to deal with significantly less equations. And also the other very important thing we were able to figure out is what makes spherical, any type of warp drive, actually in our case spherical warp drive, to require positive or negative energy. And I think this is a huge breakthrough, because now we understand what we have to put in the system to make the system require positive or negative energy. And to your point, now we're exploring all these possibilities in a new article, which we're going to submit this week. So we're going to share with you guys whenever it gets published, hopefully in the next 2 months.
Yep, that's right. That's right. Basically, this the general idea, and uh, yeah, there are some a message here that is, what is it with the word drive that if you write it in this symmetry, it works. So it is something that is hidden in the coordinates that you use, or is it something in the transformation that we are missing? And this is something that we have to figure out. The point is like we find that these things work, and we are already exploring why this symmetric, spherical symmetric word drive work very well, and what is the difference with other word drive that are around in the literature.
So Nelson, I think it's a great work. So guys, please check the article. Do let us know if you have questions. I think it's really, really major step forward for building something we can test in a lab, and this is something we're going to try to do in the next year. But Nelson, is there anything else you want to share?
Which well, maybe I can share that if you if you saw this, we don't have here heat fluxes, we don't have electromagnetic fields, we don't have any classical fields, even less quantum fields. This is that's more complicated, but any classical field you want to add here in the system is going to give you some advantage possibly, and also heat fluxes. And in order to do that, we probably have to modify the metric a bit, and that's very exciting because as you saw in here, we just are using the most simplified version that we can use. It's just a simple fluid with anisotropy and a spherical symmetric word drive. And the interpretation is more or less quite clear. We have some numerical solutions already, and but we are working on adding more and more, enrich more the content, the matter content we have, and that's as Bailo just said. We believe we can get something that is a point to start some testing, some experimental testing.
Right. So Nelson, I'm going to share a news here with the people which are still listening. So thank you very much for staying with us for that long. I know it's we're discussing something which is not that easy to digest. So we got a patent for the warp drives, and to Nelson's point, we put together the equations for the warp drive, the electromagnetic fields, radiation, heat fluxes, anisotropies together. So and we put them in one consistent framework, which is a huge step forward because all of the things I just mentioned are things we can test in the lab. So we have them in one complete set of equations, one framework, which is super exciting.